Hello students. In this lesson today, we're looking at calculating the volume by rotation. So we'll start by deriving the rule and then we'll work through some basic examples. So we'll start with the idea of volume by rotation. So if we can consider a two-dimensional plane with an x and a y axis, and on that plane we can create some function and we'll call that f of x. When we're thinking about this concept of volume by rotation, we need to have a function that represents a radius. So if we're rotating about the x-axis, then we've got a bunch of different radii, which relates to an x value being subbed into that function. For each of those radii, if we rotate them about 360 degrees, then we get a circle. So if we use that same radius, we rotate it about, we get a circle, and the extension then of that creates a three-dimensional shape. If we looked at that same function and inverse and looked at it as a function of y, then we can do a similar thing, and we can look at these values here as representing the radii. If we extend them about 360 degrees by rotation, then what we get again is the outline of a shape. Now, using integral calculus, if we focus on these cross-sectional areas as our base function, then we can end up with an exact volume of the shape that's created. Okay, so that means that when we're defining a general rule for the radius about the x or y axis, what we essentially need is to look at an area function relating to a circle. So pi f of x squared. So this f of x is a function that represents a radius at any point in time. So now that we can define a rule for the cross-sectional area, the volume is generally a product of the cross-sectional area and some height, the height being represented by x in this case. We can say that the volume is the integral between b and a of our cross-sectional area with respect to x. And so that means that our volume will be between b and a of our pi f of x squared with respect to x if we're rotating about the x-axis, and it will be the integral between b and a pi f of y squared with respect to y if we're rotating about the y-axis. Okay, so these are our base rules. We can move that pi in front, but this is basically what we're going to use to find our volume by rotation. So in this first example, we've been asked to find the volume of the solid revolution formed by rotating the curve y equals x cubed about. Okay, so this first one, we know if we look at the function y equals x cubed, this is what it looks like. And because we're working between 0 and 1, we're looking at these radii and therefore this shape. So this is a shape, the three-dimensional shape we're looking at. So our f of x is equal to x cubed. Our volume between b and a will be pi f of x squared with respect to x, so pi r squared. Okay, so that means our volume is between the bounds 1 and 0. We can move our pi out in front. Now f of x is x cubed, so f of x squared will be x to the power of 6 with respect to x. So our volume will be pi multiplied by x to the power of 7 on 7 between 1 and 0. And that means we have pi 1 to the power of 7, which is 1 on 7, subtract 0. And so our answer is pi on 7 units cubed. When we look at b, and now we're looking at rotating about the x-axis, we need a function of y. So to get that function of y, we've already got y is x cubed. We can isolate our x, so we get x is equal to y to the 1/3 So that means our f of y is y to the 1/3. Our volume will be the integral between b and a of pi f of y squared with respect to y, which means we've got the integral, because the bounds are 1 and 0 again, 1 and 0. We can move the pi in front, and we have y to the power of 2/3, because squaring, we multiply that fraction by 2 with respect to y. So we have pi. The integral of y to the power of 2 on 3 is y to the power of 5 on 3 over 5 on 3 between 1 and 0. So that will be, when we divide by 5 on 3, we multiply by 3 on 5. So we have 3y to the power of 5 on 3 on 5 between 1 and 0. And therefore we end up with 1 to the power of 5 on 3 is just 1. So we have 3 on 5. And then we subtract 0. So our final answer is 3 pi on 5 units cubed. Okay, so you can see two simple little examples there using y equals x cubed and rotating about the x-axis and y-axis between 0 and 1, and the differences between the volumes formed. So we'll continue moving forwards. In this second example, we're looking to find the volume of the solid of revolution when the region bounded by the graphs of y equals 2e to the 2x, y equals 1, x equals 0, and x equals 1 rotated around the x-axis. Okay, so if we can sketch this out in 2 dimensions first, this will help us visualize. Y equals 2e to the 2x is an exponential. We're bound by this function y equals 1 as well. So it's y equals 1. And we're rotating between x equals 0 and x equals 1. So radii will be between these two. And it will create a shape with the center hole missing, because it doesn't include that y equals 1 section that was cut out. So I apologize for the dodginess of my sketch, but essentially we're looking at taking this shape and rotating it about this axis. So obviously the opposite side of that, and that's rotated around 360 degrees. So the total volume in this case will be one volume take away another. So we've got the volume for the first function, so volume 1, and we're subtracting volume 2. So it makes sense. They're both between 1 and 0. We'll say b and a, f of x squared multiplied by pi dx, where we can write it two ways. We could say this is pi between 1 and 0. We have 2e to the 2x, 2e to the 2x squared with respect to x, subtract pi between 1 and 0 of 1 squared dx, or we could put that all together and we can say that's pi, the integral between 1 and 0 of 4e to the 4x subtract 1 with respect to x. So if we bring it all back together, 2e to the 2x squared is 4e to the 4x, 1 squared is 1, and since they've both been rotated about that axis, we can look at the difference of those as our f of x. So now this is simply going to be pi. Integral here will be 1/4 4e to the 4x, which will just be e to the 4x. Subtract x, and we're between 1 and 0. So we've got pi e to the power of 4 take 1, and then subtract e to the power of 0 take 0, and we end up with pi e to the power of 4 take 2, as e to the power of 1 is 1 units cubed. And so there's our volume, e to the power of 4 take 2 multiplied by pi units cubed. Okay, so when we look at the next example, it says the shaded region is rotated about the x-axis, and we want to find the volume of the resulting solid. So that means we're taking each of these functions combined and rotating about the x-axis. So it's the same idea. We can say that our volume, and we need to find this intersection point, our volume will be the integral between b and a of f of x squared dx multiplied by pi, and subtract pi, the integral between b and a of g of x with respect to x. Okay, so we need to find that intersection point. So to find the intersection, we can say that g of x is equal to f of x. So we have x squared is equal to 2x, and therefore x squared take 2x is equal to 0. So x take 2 is equal to 0, and we have our intersection points, which is x equals 0 or x equals 2. So now we can put this together and we can say this is pi. We're working between 2 and 0. Now f of x squared is 2x all squared, and we're subtracting g of x squared, so that's x squared squared with respect to x. So we have pi between 2 and 0 of 4x squared subtract x to the power of 4 with respect to x. Okay, so now we can perform that integral. We've got pi 4x cubed on 3 subtract x to the power of 5 on 5 between 2 and 0. And so that means we have 4 multiplied by 8, which is 32 on 3. We have 32 on 5, and we'll subtract 0. 0 to the power of 3, 0 to the 5 are both 0. We end up with pi multiplied by, now if we get a common denominator here, it will have to be 15. So 32 multiplied by 5 is 160 on 15. And 32 multiplied by 3 is 96 on 5. So we end up with an answer of 64 on 5 pi units cubed as our volume of revolution between those two functions and the intersection points. Okay, so in this example, we're looking at the solid formed when the region is bound by the x-axis and the graph of y is equal to 3 sine 2x. So that means we're going through the first half of a sine graph because the period is halved. So between 0 and pi on 2, we have this section of the pi graph where it goes up to 3. Now again, we're rotating about the x-axis, so we need our function, which is f of x. So f of x is equal to 3 sine 2x. It's just this area rotated about, so we'll get a three-dimensional shape that represents that rotation. The volume will be between pi on 2 and 0 multiplied by pi of f of x squared, which is 9 sine squared 2x with respect to x. So the difficulty is that this integral, the integral of 9 sine squared 2x with respect to x, we'll have to use trig identities. So if we consider cos 2a is equal to 1 take 2 sine squared a, then 2 sine squared a is equal to 1 take cos 2a, and sine squared a is equal to 1/2 take 1/2 cos 2a. And that means that our integral up here will be the integral of 9 on 2 subtract 9 on 2 cos 2a, where a is 2x, so that will be cos 4x with respect to x. Therefore our integral will be 9 on 2x take. Now we'll also have to divide by 4 here, so it will be 9 on 8 sine 4x plus c. So when we put this back in, we've got the volume is pi multiplied by our integral, which is 9 on 2x, take 9 on 8 sine 4x between pi on 2 and 0. And so we have pi multiplied by 9 on 2 times pi on 2, subtract 9 on 8 sine Now 4 times pi on 2 is 2 pi, and subtract 0, take 9 on 8 sine 0. Now sine 2 pi is the same as sine 0, and sine 0 is equal to 0. So we've got pi. We have 9 pi on 4, and then subtract 0, and we end up with 9 pi squared on 4 units cubed as our volume. Okay, so when we look at our final example, we're looking at the curve y equals 2 sine to the negative 1x, rotated about the y-axis to form a solid. So we know what an arcsine function looks like. Our arcsine function looks like that between negative 1 and 1, and in this case it's between 0 and pi on 2 times 2, so that is pi here. Now as we're looking at rotating about the y-axis, we're interested in this area here, and so that means we need to find our f of y function, so we need to inverse this. We've got y is equal to 2 arcsine x, and so that means we've got y on 2 is equal to arcsine x, and x is equal to sine y on 2 as our function, our f of y. So therefore our volume will be between the bounds pi and 0. We'll multiply by pi, and we've got our function f of y squared with respect to y. So we've got pi, the integral between pi and 0. We've got sine squared y on 2 with respect to y. Now obviously this is a more complex integral, so we can consider over here the integral of sine squared y on 2 with respect to y, and we can say that is the integral of 1/2 subtract 1/2 of cos 2 times a, and 2 times a will be 2 times y on 2, which will be just cos y with respect to y, and therefore this will be 1/2 y subtract 1/2 sine y plus c. So there's our integral, and that means that our volume will now be pi multiplied by 1/2 y subtract 1/2 sine y between pi and 0. So we've got pi multiplied by 1/2 times pi, subtract 1/2 sine pi, and subtract 0 and 1/2 sine 0. Now as both sine pi and sine 0 are 0, we've got pi and then multiplied by pi on 2. So we end up with pi squared on 2 units cubed as our volume. Okay, there was some added complexity in here. We had to inverse that original function to find our f of y as we were rotating about the y-axis. We needed to find our new bounds, and our integral included a trig identity. So we had to rearrange that and isolate before we could integrate and find our final answer. Alright, so that concludes our lesson on volume by rotation. You can see that the process is pretty straightforward. It comes down to being able to apply these two rules, that rotation about the x-axis and rotation about the y-axis. Everything comes back to that. So recognizing you need a function with respect to x or a function with respect to y, whether you're rotating about the x-axis or the y-axis respectively. Making sure you've got the bounds right. So if we're rotating about the x-axis, we need our bounds to be between 2 points on the x-axis, and if we're rotating about the y-axis, we need our bounds to be between 2 points on the y-axis. Okay, so that concludes this lesson. Make sure you practice this process. Thank you for listening.